Let's begin by talking about the graph types that apply to single variables. Now, single variables by themselves don't answer very interesting questions typically, at least not by themselves. But graphing single variables is a useful way for exploring your data set. You might not include these kinds of graphs in your final product in the paper you publish or whatever, but you do need to understand your data individually by variable, and these are great graphs for exploratory data analysis. What if we have a single categorical variable? As an example, let's take the mother's race. Now, one thing that's important to point out here is that the race in this data set is recorded in a very blunt sort of way. It's recorded as white, black, or other. Now, this was 1986, but nevertheless, I think it's clear that this is maybe not the most effective or the most correct way to think about race. It's also not completely clear whether the race variable was self-reported, whether this was written down by a nurse or a doctor or someone else. So without more information about this, we're not even really sure how to interpret this. So, and of course, the other category is literally othering an enormous group of people who don't fall into the first two categories, white or black. So kind of keep that in mind as we look at this variable. Probably the single most effective thing I can think of to do with a single categorical variable is just to produce a frequency table. After all, with categories, kind of the only thing you can do is just count. That's really all there is to do. And so you can see this frequency table shows the three categories, and it counts the number of women who are classified into these three groups, 96, 26, and 67. The graphical analog of a frequency table is a bar chart. The bar chart is fine insofar as it goes. One thing to consider, though, is an interesting concept that was first coined by a pioneer in data visualization research named Edward Tufte. And Tufte talked about the data to ink ratio. The way of thinking about that is how much data is being demonstrated and how much ink is spilled in demonstrating that. So obviously this is a computer screen, so this isn't real ink, this is virtual ink, but a bar chart has a lot going on here. There are the big dark bars, there's backgrounds, there's axes, there's tick marks, there's all sorts of stuff in this picture to really only illustrate three numbers. The three numbers of the frequency table, 96, 26, and 67, are the heights of these bars. The bars give you a nice sort of quick visual impression of the size of these three categories, but it does spill a lot of ink to do so. So that's something to keep in mind. Is the bar chart really much more effective than the frequency table at illustrating what you want to illustrate? There's definitely a place for bar charts in the world, no question, but keep that in mind as you're creating visualizations for yourself. Now, people also talk about pie charts a lot. A pie chart, as everyone I think knows, is a way to illustrate your data as a percentage of the total. So now we think about the pie as 100%, and the pie chart divides up into the percentage of the mothers who were white, the percentage of the mothers who were black, and the percentage of the mothers who were classified into this vague other category. And for illustrating percentages, there's nothing specifically about a pie chart that's wrong, but I do indicate that there's a danger here. And the danger comes from the fact that many researchers have discussed how pie charts are maybe not as effective as we think that they are. One of the reasons for that is that our eyes are not well attuned to seeing angles, certainly not as much as they are to heights. So when we look at a bar chart, it's extremely obvious when bars are taller than other bars. Even when the bars are close to the same height, it is very clear when one bar is even slightly higher than another bar. Now, in this particular pie chart, which is a very simple one with three groups of differing sizes, it's pretty obvious what's happening here. But if you had a data set where there were several categories that were roughly equal, it's not so clear how to measure the sectors of that circle with our eyes. We're just not as good at doing that. So opinions on pie charts are a little bit mixed, but for the most part, people agree that the pie chart is maybe not the most effective thing. Now, if you really want to see percentages, There are answers that a pie chart can answer that a bar chart isn't as easily answerable. So for example, if I asked if the percentage of white mothers in this data set was more or less than 50%, you can see that in this pie chart. It's slightly more than 50%. The bar chart doesn't show that so well. In order to answer the question in the bar chart, you would have to sort of take the black and other bars and you would have to stack them on top of each other in your mind and then see if that stack was taller or shorter than the bar height for the white group. So yeah, in that sense, there is one sort of use for a pie chart. But even then, I think that there's more effective things that can be done. For example, why not just create a relative frequency table? Just like a frequency table is probably the most efficient way to summarize categorical data, a relative frequency table does the same thing, only with percentages instead of counts. And it's very, very clear that white mothers account for slightly more than 50% of this data. So for my money, frequency table and or a relative frequency table are just fine. They're great options for this data. Now, I've linked to an interesting resource, and I'll include all the links from this set of slides in the description as well. Here's how you can improve a pie chart. If you have a pie chart and you want to improve it, at least here are some of the steps that you can take. So let's click on this and see what we can do. All right, so this starts off by removing a lot of the extra cruft, a lot of the extra just stuff that's cluttering up this picture, right? We remove the 3D. You should never create 3D visualizations. They're terrible for lots and lots of reasons that we won't get into. All right, we're still removing pieces of this chart. Oh, I see. Yeah, the effective way of fixing a pie chart is to actually create a bar chart. There you have it. All right, so that's just a little humorous interlude there. If you want some evidence, there's lots of articles online about what's terrible about pie charts. Again, these 3 resources in the top will be linked in the description. To be scrupulously fair, I did find just a couple of people, not very many out there, who are ardent defenders of pie charts. Here's a link to one. Why Tufte, that's the same Tufte as I was talking about earlier with the data to ink ratio, why Tufte is flat out wrong about pie charts. I'll include the link, but spoiler alert, basically the conclusion of this article is that pie charts are good because business people like them. And therefore we should use pie charts because that's what business people like. I don't find that a very compelling argument. I get that communication with certain groups is important and you want to communicate the language of those groups, but my mission is to educate people about the pros and cons of these kinds of graphs, including pie charts especially, so that we can have everyone be a little bit more educated about that and use more appropriate types. So I'm not saying never use a pie chart, but I'm saying you should think very, very carefully and do some research about the disadvantages of pie charts before you really commit to using one. And if you do commit to using one, make sure you're using it for the right reason. Okay, what if we have a single quantitative variable? What do we do in this case? As an example, let's talk about infant birth weight. Notice that I've mentioned in this slide that this is measured in grams, so that makes some sense of the fact that these numbers are recorded in the thousands, right? So this is clearly a numerical variable. It has numbers. There are units of measurement. Another test that I use for numerical data is, does it make sense to take the average of this pile of numbers? Is that average a meaningful quantity to report? And yes, I would say that the average birth weight is a meaningful quantity to report. So this is very clearly numerical data. And for my money, the histogram is the best way to visualize a single quantitative variable. Here's how histograms work. If you look across the x-axis on the bottom there, the horizontal axis, you can see that the range of birth weights in the data are represented there. At the low end, somewhat below 1,000 there, down to about 500. At the upper end, up to about 5,000. And so at a glance, you can see that the birth weights are somewhere below, start from somewhere below 1,000 and go all the way up to somewhere slightly shy of 5,000. And then you divide up that axis into some regions, some what we call bins. So as an example, take a look at the region between 2,000 and 3,000 on the x-axis. You can see that there are 4 bars squeezed into that region between 2,000 and 3,000. So therefore, what we conclude is that each of the bars of this histogram are exactly 250 grams. So, for example, the first bar that's sitting right above the right-hand side of the tick mark for 2,000. Okay, so that would represent the range of values from 2,000 grams to 2,250 grams. And the idea is that we go through our data set and we count up all of the babies whose birth weights lie between 2,000 grams and 2,250 grams. Okay, and when we count them up, we come up with something like 14 babies, right? And so what we do is we put a bar there of height 14 to show how many babies lie in that range of values. The next bar over to the right is quite a bit taller. That one will represent 2,250 up to 2,500 grams. And I don't have the exact number on the chart, but it looks like it's over 25, so maybe 26 babies are in that range. So what you want to do with a histogram is after you divide up your data into these bins and then you count the number of babies in each of the bins and you graph them, you want to kind of step back from the graph a little bit. And I apply what I call the glasses test. I wear glasses because I have very poor vision. And if I take off my glasses, the whole picture gets just a little bit blurry. And if you have good vision, you maybe can just squint your eyes a little bit to make it a little blurry. The individual little ups and downs between the bars are not that important. What's important is the overall shape of this histogram. So what I see when I take off my glasses is I see a big peak, one big peak in the middle. This is a unimodal distribution, which means that there's one mode. There's one place where most baby weights congregate. It's not a specific number. It's kind of a range of values. The maximum number of babies is somewhere between about 2,000 and 4,000 grams, centered maybe around 3,000 grams. So the bulk of the babies, the majority of the babies are somewhere in that range, right? That's kind of the average birth weight in this data set. The other thing I can note is that this graph is relatively symmetric. I don't see a long tail on the left or on the right extending out to one side or the other. So instead of being skewed, I would say that this graph is relatively symmetric, right? So it's unimodal, it's symmetric. The other thing you can see from a histogram are if there's any outliers. Are there any points that are little short bars representing maybe 1 or 2 babies that are really, really far away from the bulk of the data? I do see some short bars on the left and on the right-hand sides, and those do represent very low birth weight and very high birth weight babies, but they're not very far away from the rest of the data, so I don't know that I would necessarily consider them strong outliers. If I had a little bar that was clear out at 10,000, let's say, well, yes, that would be an extreme outlier relative to this data. The definition of outliers is a little bit fuzzy, and ways of calculating outliers, there's lots of different ways of doing it. So mostly I just want to take kind of a qualitative look at this picture and just say, yeah, it's unimodal, it's basically symmetric, and I don't see any evidence of really strong outliers here. And those are the things that you can see with a histogram. You can also take those numbers and kind of put them in tabular summaries. I don't prefer this because I think these are a little bit hard to read. But for example, you can look at percentiles. So in the middle of this chart, the 50th percentile is 2977. That would be the median. That's if you were to line up all of the babies from lightest to heaviest, the very center of that group, the middle baby would weigh 2977 grams. So that's the 50th percentile or the median. At the low end, the 0th percentile, that's kind of a weird way to say it, but that's just the minimum. 709 grams is the smallest baby weight. Up at the very top end is the 100th percentile, but really that's just the maximum. The maximum baby weight is 4,990 grams. And then you can see there's various other percentiles. The 0, the minimum, the 25th percentile, sometimes called the first quartile, the 50th percentile, called the median, the 75th percentile, called the third quartile, and then the maximum. So those 5 numbers, 0, 25, 50, 75, and 100, constitute what is generally called the 5-number summary. And you can kind of get a sense of the middle of the data and the range of the data by looking at those 5 numbers. Occasionally, you will also see other percentiles represented in this chart. I've put the 5th percentile and the 95th percentile. And those illustrate at the extreme ends, if there's a big difference between the minimum value and the 5th percentile, then that may be evidence of outliers, possibly. The 5th percentile is 1801, so only 5% of the babies are less than 1801 grams. The lowest is 709, which seems like it's maybe a little bit far away. I would want to look at a picture to see if that qualified as an outlier. The 95th percentile is nearly 4,000 grams, 3997, and that's a little shy of the maximum, which is 4990, which is again another reason to look at a picture and see if those top and bottom baby weights are outliers relative to the relatively extreme values of the 5th and the 95th percentile. But again, I think that these tables they're not necessarily that easy to read, and they don't necessarily show you anything that you can't see in the histogram. Now, there's a bunch of other types that I don't prefer. I will talk about box plots in the next part of this video series. There is a use for box plots, I think, but when you're illustrating a single quantitative variable, a box plot is really just a graphical way of drawing the 5-number summary, and that can be useful, but it's maybe not the most useful thing overall. Again, I think I'd rather see a histogram. A stem and leaf plot is something that you'll see often. I'm not going to get into any details about what that is. To my eyes, a stem and leaf plot is really just an uglier version of a histogram, but there's some people who like it. Dot plots are kind of the same thing. A dot plot and a histogram really look about the same. Some people prefer the format of a dot plot, and there may be specific situations where dot plots are nice because they sort of show the discrete nature of the underlying data, but I don't necessarily prefer dot plots, and I don't use them very often unless I'm in very specific circumstances.